and talk about number 5. A survey indicates that 41% of women in the U.S. consider reading as their favorite leisure time activity. You ask them one question. Do you consider reading as your favorite leisure time activity or no? They answer yes or no. Binomial.
Or no.
They say yes, no.
Go to bed.
Okay, you don't ask them what is their favorite. Yes, is it this? Yes or no. You randomly select 4 U.S. women. Well, because you surveyed supposedly all the U.S. women, whether you did it by population or by sample, you're picking out 4 women and you're asking them if reading is their favorite activity. You're going to find the probability that exactly 2 respond yes, at least 2, and fewer than 2. God bless you. So we start like this. Do we have a binomial situation? What's N? 4. Do we have a probability of success?
41.
0.41. What's Q?
0.59.
0.59. Are these fixed? Do they remain fixed throughout the whole trial? Yep. What does my X variable represent? 0 through 4. Good. I can have 0 people say yes. 1, 2. I want everybody doing this with me, guys. 3 or 4. Now, this represents a binomial situation. So we can either use the Bernoulli's, the C. We can start like this. We have 4 things. Start with your 0. Your probability of success comes first. You want 0 of them. Probability of failure, you want 4 of them. Or you can go to your calculator. Second pairs comes down to binomial PDF. Not the CDF yet. I'll show you the CDF in a second. So this is N, P, and X. N would be your 4. 0.41, make sure you give it a decimal, and start it at 0. Then do second enter, do 1. Second enter, 2. Second enter, 3.
For 0, it'll be 0.121.
0.121.
For 1, it'll be 0.337. 2, it'll be 0.351. Then the next one will be 0.163. Then the next one will be 0.028. And that's it.
You have more than that? Okay. Alright. Check and see that you get this. These probabilities should equal what? 1. Sum of all probabilities equal 1. And each probability comes between 0 and 1. That defines a probability distribution. The fact that we have this is a binomial probability distribution.
Can I go to the board next to the one?
Not yet, but I appreciate your enthusiasm, because this is great. Now, this is great. I just want everybody to be able to find these too, because you did a great job. Now, I want you to make sense out of this. 41% is close to 50%, right? Look where your higher numbers lie. Almost in the middle. A little bit to the left, just a little bit. If we were to look at this, we would see a little bit of skewing in here. Now, I know this is a little bit off the track, but if you turn to the bottom of page 191, it'll kind of show you where your probabilities are skewed. If your probability is greater than 0.5, it is skewed to the left. If your probability is less than 0.5, it is skewed to the right. What do you think it would be if your probability was equal to 0.5?
Right in the middle.
So it would be what? A normal curve, a symmetrical curve, a normal curve. It would be a perfect, nice little curve. Now, watch. If I made this graph, and I did 0, 1, 2, 3, 4, my higher numbers would be over here. 121, 337, 351, 163, and 028. It's going to be a little bit to the right. because my probability is less than 0.5, not a lot less. It's almost approximating a normal curve, but a little bit of skewing. My higher numbers sit closer to here than they do down here. And you can kind of see this one and this one are not the same, 121, 028. So it's a little bit of skewing to the right, which makes sense. If your probability is strong, then your higher numbers are going to be in this part over here. If your probability is a strong one, right, you would expect more people to say yes. If my probability that a woman would say yes to this question was 0.7, I would expect more people to say yes the more people I ask, right? So my skewing would have a left tail. It would be higher on the right-hand side. Right? Make sense out of your numbers. I just wanted you to be able to see that. We talked a little bit about that yesterday. Now, did everybody get this part? Okay, hang on one sec. Everybody get this part? No, anybody have a problem? Okay. Question there?
Does every graph have a skew? Like, I mean, it's like throughout the whole year, like every graph you talk about.
Except your normal curve. Your normal curve has no skew because it's exactly in the middle.
But I mean, like throughout the whole year, like we just talked about, like, how it's always skewed to the left, skewed to the right.
So far, the ones we've looked at have been skewed one way or the other. When we get into the next chapter where we just talk about the normal curve, then we just deal with the regular type curve. There's not a lot we can do with the skewed curve in terms of, you know, how we found the mean, the median, the mode. We looked for where that lied on the curve. But we can relate it to your probability as well. So whenever we can, we throw that in at you.
Okay.
Good observation. Now, from this, you can answer these questions from your table. What is the probability part over whole, that exactly 2 of them responded yes? So I come to my 2, and there's my probability. You already found it. So my probability is 0.51. 0.351. Now, what is my probability that at least 2? What ones am I looking for?
2 is below.
2, well, think of at least $2 in your pocket. What do you have? 2 or more. This means this is the least you can have, 2. 2 or more. Think money in your pocket because it's easier to relate. If I have at least $2, I have 2 or more. So we're looking at 2 or more. Now we can certainly just add these pieces together. And come out with an answer. Okay? You add them together, you come out with 0.542. Now, how about the other part of this? Fewer than 2. Fewer than 2 means which ones? 1 and 0. Now, I can have 2 ways to do this. I could add these 2 together.
Or you can subtract 1.
Very good. Or you could subtract 1. What case is that when you subtract 1?
I forgot what it was.
Complement case. If this is everything but this piece here, I could take what we found here and subtract it from 1. That's the complement case.
4, 5, 8.
Okay. Now, the CDF in your calculator does this part. It accumulates. CDF says binomial CDF, cumulative distribution. What it does is it accumulates from 0. It doesn't work in reverse. So if I want just these 2, in the cumulative CDF, I would put my n in, 4. I put my probability in, and I have to put the highest one I wanted to go to, 1. And that would give me the total of these 2. That would give me that one. Your cumulative works from 0 to that number. Now your cumulative is a good one if n is very large and you don't want to make a table. So like say my n was 40 people and they wanted to know fewer than 35. I could do from 0 to 34 in my cumulative. If I wanted to know 35 or more, I would use my complement case. Okay. So does that make sense? Right? I usually don't use the cumulative unless the numbers are really large. If the numbers are large, then we use a cumulative. So everybody can do this? Yes? Okay? Kinda? Alright. So you are going to do this one. I knew I'd catch it, right? Binomial distribution?
Is it?
Wait,
Is it?
can I have a minute? I want to do this on my...
Yes.
Are you supposed to ask the most like here or
Is your favorite leisure time
Oh, yeah, but here's just a little bit.
well, like, so this one is so far now you have to
Oh, you're okay. And it's close to one, but not exactly one. If you put on this, it might be 0.999, it might be 1.001. Yeah, you're exactly.
Oh,
I know, it was significant digits. If you don't, you're saying it's zero. Yeah, you have to. That's why you have to go over this. These only have to go to zero. If no, it has to be zeros, we have to go to the first significant one. That's why it goes up further. That's absolutely right. Because if you put zero, you're saying that's impossible. And it's a very, very, very small chance that it will happen.
I have a question.
I don't want to use
PDF
PDF or
set up and get the
CDF.
numbers faster.
Okay, so what did you put in?
well,
Oh,
Oh, you did the SDR? Okay, so if you do this, pull it down. You're going to change this one now to a 1. Then you change this one to a 1. And then this one has to go to a 4.
or is it still 5?
It's still 5. Now, an easier way is this. Second pairs come down to binomial PDF. This is a binomial probability distribution function. Number of trials is 5.
That's a...
Start with 0. Second enter.
That's
Change
not
this guy
right.
to a 1. Change it to a 2. Change it to a 3. A lot easier.
Wait.
would you move it to a percent?
No, keep them all decimals. Keep them decimals.
I want to wear a bow tie. Is your favorite?
Okay, is this a binomial probability distribution? We have two choices. What do they respond when we ask them if fishing is their favorite leisure time activity?
They can say yes or no.
They say yes or no. We're not asking them what is their favorite time activity. We're asking them, is fishing your favorite time? Yes or no. We randomly select 5 men. Do our probabilities stay fixed?
Yeah.
Yes. And our x goes from 0 to 5. Remember the 0 because 0 could respond, no, you could have no responses of yes. Now, if you use your binomial PDF, you're saying 5 trials, 0.21, don't forget the decimal point, start at 0, and keep changing this all the way down. So this is 0.308, then what?
0.409, 0.217, 0.058, 0.008, and then 0.0004.
Yes, now this one, thank you. This one, notice Courtney went out to the 4th decimal position. You have to go to a significant digit. Your calculator says e to the negative 4. What you have to do is move your decimal 4 positions to the left. This is the same as your scientific number. Move it 4 to the left. Yes. You just have to go to your first significant number. Like you just can't give me this as 0.000 because 0 means it's impossible to happen. So if it said 0.08 e to the negative 4 and you move this 4, 3 zeros, you can stop at your first significant number. It is so small. It's like so negligible. The only thing we can't say is it's 0. We can't say it's 0. Yeah, just get me to a significant. Approximately, these will add up to 1. Now, Lizzie's concern a little bit was with all this rounding, it doesn't add exactly to 1. You're right, it'll add to 1.0001 or 99999, but it's close enough to the 1. Exactly 2 of them responded yes. What would your probability be?
0.217.
0.217, take it right off the chart. At least 2. At least 2. Gunnar, what do you say for at least 2? Which ones are we looking at? At least, you have at least $2 in your pocket. How much do you have? 2 or more. So let's go to your 2 or more, and we're going to add those guys up. 0.283? Thank you. Now, fewer than 2. Fewer than 2 is what? Fewer than $2. A 1 or none, right? Now, again, you can add these up, or you can use your complement case. Or, on this one, you could use your binomial CDF. I wouldn't really use my binomial CDF since you already have your answers there. Probably use your complement case. Now, if we graph this guy, here's my 0, 1, 2, 3, 4. This is my probability distribution. It's like my relative.
The 0 would be high.
The 0 would be high. I'm just approximating.
1 would be way higher.
A little higher, a little lower, little lower, little lower. Where's your skew? Follow the tail. Your skew follows the tail to the right. Your skew follows the tail. Just like trace around a curve and come down off that tail. We said if your probability is less than 0.5, you are skewed to the right. And my probability is small, right? Since my probability is small, do I expect more people to say yes or less people to say yes? Less people to say yes. Okay? Kind of like at home. If you're not on the good list with your folks, the probability that they're going to say yes whenever you ask them something you want to do is small, right? So if you ask them about 5 things to do, they'll probably respond yes to maybe 1, but not too many, right? If you're on your good list and your probability is high, they'll say yes to everything, right? You're a perfect child. Can everybody do this? Yeah? Okay. Now, the last part of this, we know how to do a probability distribution, is this. If you notice, we have a very hard time putting this in your L1, L2, so we really can't do a mean, median, and mode on this, but we can do a mean and a standard deviation. Because in a binomial distribution, they don't give you a whole lot. They give you your paid, tell you how many, but they don't give us any other thing we can use. So we have these formulas that we need to use to find your mean. Notice we have no other way to make a table, to add them up, to take your probabilities, to add them up. We can't do your P of X. We could do your X times P of X. We could get your mean there. But it's far easier to use these formulas. Mean is N times your probability of success. Your variance is your N times P times Q. And of course your standard deviation is just the square root of your variance. Okay, so those are the 3 formulas that we're going to use to calculate your mean, your variance, and your standard deviation. And you have to, in this case, you have to calculate your variance first, then take the square root of it to get your standard deviation. So let's take a look at an example, and it will make more sense. In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, the variance, and the standard deviation for the number of cloudy days in June. If I didn't have a formula, I'll get it to you one second, Darian. If I didn't have a formula, how do I find the mean? Did they give me the temperatures for every day in June? I can't add them up. I can't do my standard deviation table. I can't put them in my L1.
Wait, is June have 30?
No, because we're only asking for the days in June,
So.
but we want to know what was the mean.
30 or 31.
Well, we want to know the mean number of days for June. Like what would the percentage be? We can calculate the mean, but the standard deviation would be a little difficult. So we're going to use these formulas. The best way to start is just to pull out your information. P is 0.56. So, yeah. 192. So what's Q if P is 0.56? 0.44. 1 minus your probability. And what's N? 30. How did you get that? There's 30 days in June. Good, they were kind of tricky, right? So, if we do this, we get N times your probability. Exactly what Lizzie said. Can't we take our percentage of the days in June? This is exactly your mean. And that was good that you saw that. I just didn't want to say yes until we kind of wrote it out. So now, there's your mean. And you do have to remember, it wasn't for the year, it was just because they wanted us to do June. And we calculate our mean. Now, your mean should be one more than your days. So your mean has to be, how many decimal places should I make my average, my mean go to? 1. Why 1? In the days, right? In the number of days, I have 5 days, 10 days. So very good. So make your mean go out to 1 decimal place. It just takes a little bit of reasoning through this part. Now, you already have this piece, your N times P. To do your variance, you have to do N times P times Q. You already have this piece. So you know it's this times this times this. You can easily just take this answer and multiply it times 0.44. You already did that part. You know this piece is 16.8. You can just multiply it by 0.44. Or just multiply them all again if you like. Either way you like to do this. This is going to come out to be
7.392.
and good, so we'll round to 1 decimal place. Now, your standard deviation is the square root of your variance. It's the square root of N times P times Q. So we know this is this.
2.7.
So 2.7 is your standard deviation.
You wrote 2.7 on the board.
I wrote 2.7. I wrote 2.8. Okay.
Bugging.
Ah. And I said 2.7, didn't I? And I wrote 8. Thank you. Okay, so we're going to use this formula to find our mean, our variance, and then take the square root and find your standard deviation. You have no other way to find it. No one's giving you all the days for each time, so we have no other way. So let's take a look at another example. In San Diego, California, 44% of the days in a year are clear. Find the mean, the variance, and the standard deviation for the month of May. So take a minute and find me those pieces. Start with your P, your Q, your N. Start with those 3 pieces of information. May has 30.
No, wait.
Yeah.
If June had 30, then May has 31.
May has 31.
You just put unleashed.
30 days. Yeah,
Maybe it's keeping you honest. You know that little line, yeah. I always remember that one. That works good? Oh, wow.
Wait, wow.
That's pretty cool. I never thought of doing that either. She does it in between her knuckles, in between her fingers.
Oh, yeah.
January, February, March, April, May, June, July, August. August has 3rd February. Oh, and you do the other hand. Okay. Oh, very good. That's cool. Okay, so fill these in.
You're not checking this, you know what? You split the numbers.
I never knew that one. Okay, you're gonna have to remember these n times p. It's not so bad because they're the only pieces of information you can get out of here. So you can't keep multiplying n times p times q to get 3 different things. So n times p for the first time around. And again, we're going to round your mean to 1 decimal place. What'd you get? So on the average, I would expect 13.6. It's the percentage of the days there. And that's all this is, a percentage. And then take 13.6 times your Q. And what does that give me? 7.6, that's my variance. And just take the square root of that.
2.8.
2.8.
You didn't even let her finish writing it.
Because I didn't want you to.
He didn't want me to make a mistake this time.
Well, no, it's.
I must have been
every
psychic
time
about
I
the
try to
2.8.
answer a question,
Someone else jumps you, right? They're quick. They're quick. Joe, you got to be on the ball. All right. So any questions for this? No? All right. Now, tomorrow